So we stopped here last time. We were discussing a random access memory. Just let me repeat the last thing I was saying. Basically, we have an array. We have some rows that are called word lines, and then we have some columns that are called bit lines. At the cross of a word line and of a bit line, we have typically a memory cell which is able to store 1 bit of information. Then we have a word decoder and a bit decoder. The inputs of these decoders are the addresses, some bits of the complete address of the cell. And the important thing to remember is that at a given time only 1 word line is active and only 1 bit line is active, so that only the memory cell which is at the cross of the active word line and of the active bit line can actually be accessed. So it can be written or it can be read. Okay. Now, what I want to stress a bit is, from the electrical point of view, what happens if we consider a single bit line. So for the moment, let us focus on a single bit line, and let's look at the problem from the electrical point of view. If I look at the cross-section of a bit line, what I see is a rectangular cross-section. This is typically a metal line. That is the actual bit line, which is separated through an insulator from the substrate. This separation is a few hundred microns typically, and is a dielectric or insulator. The two words are synonyms. Now, so this is the let me use some color. So this is the cross section. If I look from the top, and if I draw the top view of the bit line, I have a long interconnection. So typically I have something like this. Let us assume that this is longer than the space we have here. So this principle is something much longer, a long metal line. The typical length can be something like a fraction of a millimeter. For simplicity, let's write something like 100 micron. And the width, this width is typically 0.1 micron, so 100 nanometers. So the practical thing to understand is that this bit line will have a capacitance with respect to the substrate, because the substrate is conductive, and also, of course, the metal line is conductive. So we have two conductors separated by an insulator, and therefore we have a capacitance. And of course, it will also have a resistance, because it's a long conductor. But let's focus on the capacitance first, because it's more relevant. So before we write the capacitance, you have to think that at regular positions, the bit line is crossed by metal lines. Okay, and actually, what we have is that every few hundred nanometers along the bit line, we have a contact with the substrate. So these are contacts. For example, in the case of a DRAM, we have the word line, so that the situation is clear. Then we have the word line goes. No, let me. Maybe it's clearer if I draw this way. We have the word line and we have the bit line. And then at the cross, we have that the word line is connected to the gate of an N MOSFET, and the source of the N MOSFET is connected to a capacitor, and the drain is connected to the bit line. So we have one contact here and one contact here. And so this contact is exactly the contact that from the circuit point of view is plotted like here. So we have the metal line which contacts the drain of the MOSFET. So something like this in cross section. We have the bit line, and then a via, which is written as via in Italian, which is typically a metal layer which has to connect two different layers. So this is the bit line, this is the via, and then the via connects the bit line with the substrate. For example, we have the N plus diffusion of the drain. So this is what happens exactly in this position. It is the cross section of the bit line in the position corresponding to the contact. So now I think it is clear the situation. What is important is to evaluate the total capacitance of the bit line, because it's going to be quite relevant for the operation of the memory. So this bit line has a capacitance per unit area which is something like, let's call chi sub, because it's with respect to the substrate, is something close to 100 attofarad per micron square. So this atto prefix is written with an A and means 10 to the minus 18. Okay? A means 10 to the minus 18. So the total capacitance is something like, let's call it C tot. We have to sum the capacitance of the bit line, which is C sub, the value before, times W times L, the area of the place, the length and the width of the metal line, plus we have to consider the capacitance of each contact. And in order to compute the capacitance of each contact, we need to know, let's call it C contact times N, the number of contacts that we have along the bit line. Now, we can provide these numbers, typical values. So C contact typically is something like 0.4 femtofarad. So it's much larger than the capacitance per unit area for the same area, because we have, let's say, really in this case we have the capacitance of the contact. We have a depletion region under the drain, and this is the capacitance of this depletion region. And N is equal to the number of contacts that we can compute if we know the distance between two different contacts. Let us assume that this distance is D, and it's typically something like 400, 0.4. Let's write 0.4 micron. So N is L over D. So 100 micron divided by 0.4 micron is 400. And then if we make this calculation, at this point we have everything, we end up with something like C tot equal 101 picofarad. Okay, so femto means 10 to the minus 15, and pico, of course you know this, it's more common, means 10 to the minus 12. So 100 picofarad, more or less, which is not small. Why is this important? I want to stress the fact that each cell, which contains one bit, is connected with a much larger capacitance. And this is something critical in the operation of the DRAM, because, for example, as we will see in a moment, is the reason why for a DRAM we need the continuous refresh of the information. Okay? This is something we also need for SRAM. For SRAM we do not need actually continuous refresh, but we need to refresh the information when we read it. Okay, so just the important thing to keep in mind of this of this image is that we have a way that allows us to compute the capacitance of the bit line, that this capacitance is proportional to the number of word lines which cross the bit line, and that this capacitance is large. 100 picofarad in an integrated circuit is a large capacitance. I just want to anticipate two things that we will discuss later. First, this is the main reason why a refresh is needed often, especially every time we read the memory. This is true both in DRAM and in SRAM architectures. And the second aspect is that actually the considerations on the capacitance limit the maximum size of the memory bank that we can make in practice, and that we can have in practice. So these considerations have an impact on the memory architecture. So let's look at this problem in more detail. So just to look at things in context, let's consider again a DRAM. As I mentioned before, we have a memory cell at each crossing of a word line with a bit line. So, at each crossing we have an NMOS transistor connected like this and a capacitance. So we have one transistor plus one capacitance per bit. Okay. You know the principle of operation of a DRAM. Basically, the information is stored in terms of the charge on the capacitor. So if the capacitor is completely discharged, we have a 0. If you have a charge Q on the capacitance, we have a voltage, positive voltage on the capacitance, and then for example, if we activate the word line, we can read this voltage from the bit line, which is connected to the capacitance. Okay. This is the principle of operation. So for every bit of information, we need a MOSFET and we need a capacitor. Luckily, from the technological point of view, there are ways to build the capacitor vertically. So basically we draw a hole in the substrate in which we fabricate the capacitor, and in this way the size of the capacitor is not too large, and so the DRAM can be made in a quite compact way. We shall see how the capacitor is made later. Now the problem is this, let me draw it with another color, this total capacitance of the bit line. The C tot. Because what happens is that, let me just explain the situation from a qualitative point of view. Of course, you have a given charge on the capacitor. If you, with the word line, switch the MOSFET, turn the MOSFET on, this charge goes onto the bit line. But of course, since the bit line has a large capacitance with respect to ground, the total charge which was on the cell capacitor C is shared between the capacitor C and C tot. So the variation in terms of voltage that you can observe on the bit line is practically very small. Okay, this is something that you should. Let us assume that we have a charge Q. Q is the charge initially on C. Okay, so this charge Q over C gives us the voltage of the voltage on the capacitor. On the capacitor C. So this is V. Okay. Now, when we connect the capacitor C with the bit line, the same charge is shared between C and C tot, and of course C and C tot are in parallel, so they are equivalent to a capacitor of capacitance C plus C tot. Okay? So, the voltage on the bit line is, let us call V prime, is equal to Q over C plus C tot. But since the total capacitance is much larger than C, this voltage V prime is much smaller than V. And I mean, it really can be very much smaller because, for example, V can be 1 volt, but the total capacitance is, let's say, 500 times the single capacitance of the memory, and then this volt is divided by 500. So we only see a 2 millivolt variation on the voltage of the bit line, which is, of course, too small for a voltage that can be a valid digital signal. Okay, this is the huge problem of DRAM. For this reason, we need a very specific circuit which is able to measure, to detect the small variations of the voltage on the bit line, and to interpret this variation as a logical 0 or a logical 1. And interpreting this variation can restore the voltage on the bit line to VDD, so the value which is 1, or exactly 0, which is 0 voltage, which is the logic 0. So the answer to this problem is the use of a sense amplifier. The sense amplifier is the circuit which is able to detect the small variation of voltage on the bit line, to understand if the information stored on the memory was a 0 or a 1, and to restore the bit line to the logic, to the full voltage of the logic value. This is also important because during the reading process, the internal capacitor of the memory cell C is completely discharged, because since C tot is much larger than C, most of the charge moves from C to C tot, and therefore we need to also restore the charge on the capacitor C. Okay? So the same problem we have for the static RAMs. Let me draw in this place. We have the circuit for the static RAM. The situation is similar. The static RAM, of course, is larger because we have 6 transistors for 1 bit. And let me just draw the circuit. We have basically 2 inverters in a loop. These are 2 inverters in a loop, which means in a latch circuit, which means that the output of one inverter is connected to the input of the other, and of course the output of the second inverter is connected to the input of the first. You know that this is a latch, and in addition to that we have 2 additional access transistors to access the memory cell. So we have a word line which goes like this and allows to access the latch, because it turns on the NMOS transistors that connect this latch with the external world. And then we have, in the case of SRAMs, we have actually 2 bit lines, because the circuit is symmetric. We have 1 bit line on the left and 1 bit line on the right. Basically, this is the bit line, and this is the bit line negated, because of course this is a latch. For example, if the latch is let me show you an example. Let me put some numbers. If this is 1 and this is 0, the output of the two inverters is 1 for the first and 0 for the second, when 1 means high and 0 means low. When the word line is high, this 1 goes to the bit line, and the 0 goes to the bit line negated. Okay? So, the bit line negated always have the negated information with respect to the bit line. Why we use two of them instead of just one? Because of the fact that we need to use also in this case a sense amplifier. This is not as obvious as in the first case, because we do not have in this case a complete destruction of the information in principle, but in practice we have it. We do not have for a single cell, but for a large array in practice we have it. Let me explain. Of course, we can highlight the total capacitance of the bit line on the left and the total capacitance of the bit line on the right, because we have it also in this case. Now, let's assume that initially the bit line is completely discharged, so is at 0 voltage. Okay? This is not what happens in practice, but just for the sake of an example, let me make this hypothesis. If the total capacitance of the bit line is completely discharged, so we have a 0 volt, when we turn on the MOSFET, because we raise the voltage of the word line, the problem is that in order to have 1 on the bit line, we need to charge the capacitance. It is not something that happens immediately, because the capacitance is not small. We need to charge the capacitance, and in order to charge the capacitance, we need to have some current that flows in this way from the PMOS, because this is high and the PMOS is connected to the upper terminal of the total capacitance. And of course, we also have this other connection in case the bit line negated is not completely is not at a 0 voltage, but it is at an intermediate voltage. What we need to do is to connect. In order to have 0 here, we need to deplete the capacitance of the bit line through the NMOS transistor of the second inverter, which is of course turned on if the output is 0. This process is extremely slow, because the MOSFETs here are very small, and we need to do them small because we need to have gigabytes of memory. So every transistor needs to be as small as possible. But the total capacitance of the bit line is not small, because we have a large memory array, so C tot is not small, and therefore the charging time of the capacitance of the bit line is extremely slow. So for this reason, we don't do this. We don't accept this situation, and instead, also in the case of the static RAM, we use a sense amplifier, because we try to detect as soon as possible in which direction the voltage on the bit line and on the bit line negated is varied, and then we help the transition. So the sense amplifier detects the situation so that it can read the information before the charge has been completely, the charging process has been completely finished, and then actually helps this process to complete, so that we can be sure that the information on the latch is not changed. Okay? So also in this case we need, in practice, to use a sense amplifier. Okay? So now I'm going to discuss a bit how the sense amplifier works in the case of the DRAM, but you need to know that you need a sense amplifier in practice also for SRAM if you want to have a fast read of the SRAM. And you of course want a fast spread of the SRAM. Remember, typically SRAMs are used in the cache memories of processors, so you need them to be fast. Otherwise they're useless. Okay, let's focus on the sense amplifier. Now, what's the concept? First we look at the concept, and then we look at how it is implemented. So remember, this is the situation. We have a bit line which has a large capacitance to ground, and we have to read the voltage on a small capacitance in the case of the DRAM. Now, the principle is that we want to detect also small variations of the voltage on the bit line. In order to do that, first we have to precharge the bit line at the voltage value that is known, because we need to know where do we start from. And therefore the first thing is that we precharge the bit line at VDD half. Okay? And we also precharge both the bit line and also precharge a comparison bit line. Which can be, let's say, a fake bit line, something that it will not be connected to a capacitor, so something that will not change its voltage. Okay, and then we have the evolution of something like this. For example, let's assume this is the voltage VB on the bit line. So first we precharge it at VDD V-bit. Okay. First we precharge it at VDD. This is time. Okay. So this is the precharge. Then we connect the bit line with the capacitance, which means we turn on the pass transistor, and then we have something like this. For example, if the voltage is high on the capacitor, here we'll observe a small change towards a higher value of the voltage on the bit line. On the comparison bit line, we have essentially no change. This is the comparison bit line. Then at some point, so let me write every phase. During this part we activate the word line. This is the word line. And so we observe a difference. And then at some point we activate the sense amplifier, which compares the two voltages and decides that the voltage of the bit line is higher than the one on the comparison bit line, and then the value the logical value stored in the memory was 1. So when we activate the sense amplifier reads the voltage on the bit line, decides it must go high, and puts it at a high value. So it moves this to VDD. Okay. And typically for how the thing works, it moves the voltage on the comparison bit line on the other side. It puts this to 0 and the other one to VDD. So in this situation we are activating the sense amplifier. Basically we have a comparator and then we move the two voltages in two different directions. Of course, this is the example of a DRAM. In the example of an SRAM, the situation is easier because as a comparison bit line, one can use the bit line negated because it will move in the other direction, so it makes things easier. Okay, but essentially the principle is the same. Okay, so we have a precharge during which we set the voltage of the bit line to VDD, half. Then we activate the word line and then we activate the sense amplifier. After some time we can actually read the bit line because the information is full logic value, either VDD or 0. In this case we complete the read operation. Okay. Well, this is what is happening inside a DRAM every time we want to read, let's say, a memory cell. Now, from the circuit point of view, how it is done? So, now I need to draw a large circuit. Let's assume that this is the memory cell. This is the word line which arrives on the gate, and this is the bit line. Now we need another bit line. For example, a bit line which let me write it in gray. This is the how did I write before? Comparison bit line. Okay. This is the comparison bit line. I use a comparison bit line in order to have everything symmetric. The comparison bit line is connected to another set of memory cells, and let us assume that the word line in that case is not activated. So this the voltage on the comparison bit line does not change. Now what we do is the following thing. We at the end of the two bit lines have a latch, another latch made with large transistors, because we have to drive a large current. So this is connected and this is connected. This latch is enabled by two pass transistors. Let's call this sense N, and this is sense N negated. So if these two pass transistors are off, the latch is not does not have a power supply. If these two transistors are on, the latch is connected to the power supply. And then this latch is connected to the 2-bit lines. Now, then I need an additional circuit here to the pre-charge. So this is done in this way. Basically, I have here VDD half, and I have two pass transistors to connect the 2-bit line to VDD half, and also for simplicity to connect the 2-bit lines between them. Let me, okay. So, no, sorry. I cannot go back. I need to connect this way. Let's call this EQ. Okay, this is the CQ. Let us understand what we do. When the signal EQ is high, of course these three transistors in blue are turned on, and therefore this means that the 2-bit lines go to VDD half and are exactly at the same voltage. So this EQ stays for equalization. We are pre-charging the 2-bit lines at VDD half, which is the thing that I said before. Okay, so if you want to look at the timing, so let me write here EQ. These are the bit lines, and the comparison bit line. And then we need to look at the word line, and then we need to look at sense N. Okay. And we're done. So let's draw what happens. First, we need to pre-charge, as I mentioned before. So we pre-charge the 2-bit lines at the same voltage VDD. So the voltage of the bit lines at the beginning, let us assume that were a little bit different, because for any reasons they could be at a different voltage with respect to VDD half. But when the equalized signal is high, they both go to the same value, which is VDD half. Okay? So this is the pre-charge. Operation. Okay? Up to this time, the word line is down, is not activated, and also the sense amplifier is not activated. Both the signals are 0. Okay? Then, After the precharge, we have to activate the word line, as I mentioned before. So we can activate the word line, which is this one. This goes to high. Sorry, I forgot to draw the capacitance here. So what happens here? For example, if the charge on the capacitor of the memory cell was high, then the bit line moves towards a higher value, just a little bit, like this, for example, and then the comparison bit line does not move. Okay, so we have a very small variation, a few millivolts, not more than that. After we have activated the word line, we can then activate the sense amplifier. So let me write everything. So we here activate, we have done activate word line, which means the word line goes up, and then we activate the sense amplifier here. We activate the sense amplifier. What do you expect that happens here? Look at what is the sense amplifier. This sense amplifier is essentially a latch. If sense n is high and sense n negated, of course, is low, these two pass transistors down and up are short circuits, and so we have a latch which is connected to a power supply. Of course, the latch is a bistable circuit, and it will go to one of the two stable states. It will evolve to one of the two stable states. So, depending on the small difference that we have between the voltage on the input of one inverter and the voltage of the input of the other inverter, this latch will go to one state or to the other. In practice, it's the same situation that we have in this condition. Let's assume that we have a pen in the vertical position which only has 1 degree of freedom. We just, if we just move the pen in one direction, the state will evolve in one of the two stable states. The system will evolve in one of the two stable states. If we move the pen in the other direction, it will evolve in the second stable state. So the only thing that we need is that this latch is large enough and fast enough to have this evolution fast. And therefore, we end up with a very fast evolution. Here, the bit line is higher than the comparison bit line, and therefore this goes to VDD. And the comparison bit line, which is connected to the other output of the latch, goes to 0 very, very rapidly. Okay? So the word line is kept. The word line is kept at a high voltage. And it's done. And at some point we can actually read the voltage on the bit line. Here we can read. In this situation, the data is ready to be read. Okay? So I've simplified a bit the operation of the sense amplifier just to convey the main message. This procedure is something that in some way limits the velocity of the DRAM, because the sense amplifier cannot be typically there is this very general law in electronic circuits. If you want to have some robustness with respect to noise, you cannot have a very fast circuit. So since you want to detect very small variation of voltage on the bit line, we need to have a slow sense amplifier, and in order not to be too much sensitive to noise. And this ends up to be one of the main limitations of the access time of dynamic RAMs. For the static RAMs, we typically have the same situation in terms of the need of a sense amplifier, but the variation of the voltage on the bit line is larger because we have a latch which is providing the voltage, not just a capacitor, and therefore we can have a much faster sense amplifier, and therefore we have a faster read time for a static RAM. Okay, this is how things work. We make a break now, let's say a 10-minute break, and then we start from here.